Welcome everybody. Today is April the 8th, 6 o'clock p.m. We are now going to start our virtual lab session. And as usual, we'll start with the quiz first. You'll take a quiz and we'll come back again, walk you through the data sheet, how you will complete the data sheet, how to determine the formal charge, how to draw the Lewis structure for molecule. There is a handout I did send to you a few minutes ago through the email, which I believe it will help you in completing the data sheet. I do have a sets of rule. I'll walk you through how you can use those sets of rule to draw the Lewis structure for molecule and predict the molecular geometry as well as the electron domain geometry for molecule. First, before I make the quiz available, I have a couple of announcements. One is regarding the final. Final will be next week, same time, 6 o'clock. Multiple choice questions. So please plan to tune in or join the conference on time. It's gonna be about 1 hour. It's gonna be 1 hour exam. Multiple choice. Gonna do on. I'll post the exam on Canvas. Please use the step guide I did send to you or post it over the weekend. I'm still working on the data sheet pre-lab. You have submitted. Some of you have seen. You may have seen that there's some grades on the submitted pre-lab assignment on Canvas. I'll work on the data sheet over the weekend, and by next week I should have everything posted. Please send me an email to remind me if you don't see any changes or if you see that no grade has been posted for a particular pre-lab or data sheet by next week. Please do not submit. If you did not submit any assignment before the due date, do not submit on the wrong folder. For example, you cannot submit experiment number 9 work on folder number 12. It will not work that way. I want to see each assignment in its respective folder. You cannot submit pre-lab number 10 in pre-lab number 11 and assume that I received it. No, you'll see a feedback. I've uh, send a feedback to some of the students who did that. Please let me know. You cannot send, you cannot attach an email as well. Do not send your work or submit your work through the email. So that's just to remind you if you did not, or if you submit the wrong assignment in the wrong folder, send me an email and I'll respond to your email. So without wasting my time, it's now 6:03 on this end, and I want to make the quiz available. You have about 30 minutes, and we'll come back again. I'll walk you through the data sheet and how you will complete the data sheet and submit via Canvas. So please, in the meantime, look for periodic table. You're gonna need the periodic table for this lab, for the quiz, and a calculator. You're gonna need a calculator as well. Lab, if you haven't finished the quiz, I know some folks they came in. I don't know if they had internet connection issues. Please let me know after the session. Today is our last lab session. Next week will be final. This is the last lab. Please make sure you submit your work before final. And if you have any other lab other than what the folders are provided online, please do not send us an email attachment or do not submit other lab experiment or pre-lab assignment in the wrong folder. All right, I will not create those labs because if I'm creating drawing and understanding Lewis structure pre-lab, that's what I expect to see in that folder. some students, they have just been putting experiment number 10 in the wrong folder, and I had to respond back that this is the wrong assignment, and you have to resubmit your work in the right folder. If it's not available, please let me know, and I'll accommodate you. So to cut a long story short, this is the last session. Next week will be final. Once you're done with the exam next week, that's it. I'll be working on the data sheet this weekend. I still do have some hard copies to create, so some of you will see some missing crates for previous experiment and pre-lab showing up. Okay. Let's get started with our lab today, which is understanding, drawing, and understanding Lewis dot structures. Lewis was an American chemist who proposed that when elements on the periodic table react, they make use of their valence electrons, all right? And that's why this sometimes is called models and chemical bonds. You know what chemical bonds are, right? Chemical bonds, either ionic bonds or covalent bonds. In Lewis dot structures, mainly the compounds you'll handle or you look at are molecular compounds which are made only of non-metals. Using the periodic table, you don't need to write the electron configuration to figure out the valence electron. First thing, the key thing in succeeding in Lewis dot structures is determining the valence electron. You should be able to determine the valence electrons. What I want to do is share, I'm gonna share my screen and show you how to determine the valence electrons. If I look at, if you look at on your screen, let me share my screen. If you look on the screen, the valence electrons for carbon. Can you see the valence electron for carbon? See? Can you see the valence electron for carbon, please? Somebody can respond.
Yeah,
yes, thank you. So here are just few elements. For main group elements, you can use the periodic table. Main group elements are those labeled using the A. All right, it's a different case when handling the inner transition and the transition metal. So valence electron corresponds to group number, group 1, group 4, A, 5A, 6A, if you look at oxygen and sulfur. That will help you using the periodic table, that will help you in completing the box for each of the on the data sheet. That this part right here should be easier for you to determine the valence electrons using the periodic table for main group elements. And you are up. All right, you are up for all of them. So coming back to valence electrons, those are the electrons in the outermost shell when you write the electron configuration. So I don't want you to waste time and energy trying to write the electron configuration and try to find the valence electron. Just use the group number and you're good to go in determining the valence electron for an element. And for a compound, you add up just the way you find the molar mass of a compound, add the atomic masses. For valence electrons for a compound, you add the total valence electron and you have total valence electron for a compound. That is the basis for understanding Lewis dot structures. And I want to use an example in the data sheet to show you what you need to do in each section. There are 3 parts. There is part 1, there is part 2, and part 3. There is part 1, part 2, and part 3. In part 1, this is what you need to complete for every compound. This is what you need to fill in for every compound. If you look at the box right here, you need to complete each All right, you need to complete each of these boxes by filling in the information. And I'm going to use water molecule to show you how to draw the Lewis structure for the compound. Draw the Lewis structure for compound. All right. I don't want you to draw the molecular geometry that's 3 dimension. Two
Hey,
dimension
Professor.
will be fine. Okay. 2 dimension will be fine for you to complete the data. I have a summary and I'll send you. All right. I'll send you this document if you need. This is a document. I just synthesized some of the rules here, just mine, which I've over the years I've found out to be uh, easier to follow, and it's very elaborate in terms of coming up with the uh, dot structure for a molecule or polyatomic ion, right? A molecule or polyatomic ion. So first, rule number 1 here is determine the total number of valence electron in a molecule. So maybe here I can say in a molecule or poly atomic atomic ions. Polyatomic ion are those
We can't
ions.
see your screen.
You can see the screen. Okay. Let me just reshare. All right. Let me just reshare. Can you see now? Can you see this
Now
document?
it's back.
Yeah.
Yes, this is what I was talking about. Rule number 1. I synthesized these rules so as to help you. I'll send you this document as well. And there is another document here which we will come back to it later. I'll come back to other document here later. This is the document. Can you see that document?
Yes.
Yes. I'll come back to this. These are some of the notes I've seen that it's helpful in determining the Lewis structure for a compound. Let's go back to our water molecule. If I go back to the data sheet right here, I want to superimpose these rules so that we see how to answer each and every box you see here. Now, rule number 1 here is determine the total number of valence electron. And if you know from the periodic table, hydrogen, if I say hydrogen, just create this total number of valence electrons. I'll say H2O, H2O, this one is made up of hydrogen, is equals to 1 times 2. We have 2 hydrogens, and this gives us 2. And we have what? We have oxygen, which is 1 times 6. This will be 6. And we say what? We say these are 8 valence electrons. These are 8 valence electrons in water molecule. So I'll do the same thing for all other compounds. You need to be able to write the chemical formula for all the compounds, either polyatomic ion or monoatomic ion. So to get us started, I'm just gonna have 8 right here. That's how you'll fill in for each compound. You should be able to write each polyatomic ion or molecule. You want to Google out, or if you can, if you are in a position to just use the periodic table and common understanding, that's how you'll do for valence electron. Now, rule number 2, what we're gonna do in rule number 2, let me just I want to erase this. I don't want to create a mess when I scroll down to see what rule number 2 states. If you look at rule number 2, upon determining the total number of valence electron in polyatomic ion, you will draw the skeleton of the molecule, always the least electronegative being at the center. The first element you see, unless it is 2 atoms, you don't have a central atom, the least electronegative, remember electronegativity, the ability of an atom to attract electron toward itself in a covalent bond, there's electronegativity, an increase from left to right on the periodic table. So let's see the skeleton of the molecule. How are you gonna draw that? For H2O, all right? For H2O, this is how you will draw the skeleton of the molecule for H2O. We will have oxygen bonded to two hydrogens in there. This is what I call the skeleton. You'll make a connection also for other compound or polyatomic ions. So when I look at rule number 3 here, all right, draw the skeleton. We have drawn the skeleton right here. Subtract the bonding electron from the total number of valence electrons and distribute the remaining electron on the external atoms. External atoms are what are hooked up to the central. What are hooked up to the central? These are external atoms. This is what we call the central atom, oxygen. Whatever will be at the center is called the central atom. These are external atoms. So what that means, rule number 3 is it is understood that here we have two electrons right here, all right, and right here. These are two electrons, and here two electrons. Remember a single line or a single dash connection stand for a single bond, two electrons. Two lines, double bond for electron, and so forth for triple bond. So we need to subtract what is remaining. To find what is remaining, I'll subtract 4. Remember, these are the total number of electrons or valence electrons we have. We have 4 remaining. There is an exception. Hydrogen cannot have 8 electrons. I don't want to see dots on hydrogen when it is hooked up to something else. The way it is right now, hydrogen is satisfied with electrons. First priority in distributing remaining 4 electrons, all right? 4 electrons remaining. This is what remain, all right? First priority are external before you give the central atom. And when you distribute electrons, they should be paired. So I'm just gonna pair this right here and here. If I add other elements other than hydrogen, that external atom here will take first priority from what is remain after subtracting the bonding electron, after the bonding electron. So subtracting 4 here, if I subtract 4, nothing remain, all right, no more electron remain, and we just give that. So this does not help us in terms of completing this other section on the data sheet, but it's the this is what we need to complete what is remaining here. How will you do that? If I erase here so that you see, let me erase these electrons here, and that will remain. To complete electron domain geometry and molecular geometry, for these 2 items right here, you got to look at the central atom. Central atom, all right, this is the central atom. Look at what I'm doing, and it's gonna help us in formal charge as well. I'm just gonna put it in the box, the central atom right here is the central what? This is the central atom, okay? That is the central atom. And once you have that, the central atom, you will see this box right here, the box right here. Somebody is asking about the, the microphone. I guess I muted everybody. It's not gonna work. It's not gonna work. Everything is muted. So if you look at what is boxed in here, it will help you in. It will help you in understanding the molecular geometry and electron domain geometry. Once you have this configuration, you have to box this. Now, there is this handout, all right? There is this handout I sent to you through the email. This is the handout I'm talking about. This is the handout right here. A stands for the central atom. Maybe I should have this so that you see what that means right here. A, this is the central atom. B is number. This is the number of what? Number of external atoms. These are number of external atoms hooked up to the central atom. And E, all right, E stand for number of what? Number of lone pairs, not number of electrons, number of lone pairs on the what? On the central atom. It is important to understand what is meant by lone pairs. If you look at our water molecule here, we have two lone pairs. So if I move this one, my configuration for H2 here, what I circle here, superimposed on the document, I can say that this is A. Let me just use a different color. It is A for what is at the center, that is oxygen. A stands for the central atom in these notes I do have on the side. I do have it here, but I don't think it's visible. If you print it out, you may not see what it stands for, but I have it next here. So A is the central atom based on the box right here. And B, I have B and two subscripts for how many atoms on the external, hydrogen and hydrogen. That is why I say P2. And what I have on the lone pair, one pair, it is E2. I don't want you to say E4, saying that R4 electron. It stands for pairs of electrons, With this configuration right here, all right, with this configuration right here, it will help you in this document right here. I mean, electron domain geometry and the molecular geometry. How? If you use this handout right here, this handout you see here for H2O, this is where we are. If I look at this, everything will be on this. AP2 is, look at what I'm circling in red, because of this configuration right here. Because of the configuration I have here at the top, it is AP2E2. This is what I'm gonna use. And this stands for the geometry of the molecule, and this one stands for electron. And if I look at electron domain geometry is tetrahedral. This is tetrahedral, and this is, no, not that one. This is what I meant to say is it is tetrahedral. Tetrahedral for H2O is right here. Tetrahedral, this is the electron domain geometry. If you look at right here, it's talk about electron domain geometry. This is the molecular geometry, which is V-shaped right here, or pen, whichever way you use. So if I go back to the document now, all right, if I go back to the document, right here, electron domain geometry, this was tetrahedral. So you'll write tetrahedral right here, tetrahedral right here, tetrahedral, and this, I think the tetrahedral right there, and this one is V shape or pen. So if you look at how I came up with this, I used the handout to find the configuration from here, the central atom. And with that, I can use the handout to predict the shape and the shape, that is the molecular geometry, and the electron domain geometry, which is right here. Electron domain geometry is tetrahedral, and molecular geometry is what I use. And it's based on this configuration I do have here, which started from what I had to put it in a box for the central atom, with that, that take care of 1, 2, 3, 3 items so far. And you can use either the handout, or you can use this one to predict the bond angle. Here is the bond angle. It is 104.1, 104.5. And then hybridization, you have to use the handout. Let me just go back to the handout for the class. Right here, there is the table which said hybridization. I want to clear this, it's cleared, so that you see what I'm talking about. Let me just erase these we have looked at. Now, what is hybridization? If you look at what we looked at, the domains, there were 3 domains. All right, there were 3 domains for water molecule. All right, there were 3 domains, width, all right, number. You see, 4 domains because of the 2 lone pairs. We had 2 lone pairs of electron. The bond angle, 109. Molecular geometry is band, and the hybridization is sp3. So I'm going to use the number of, if you look at the what we had boxed before, all right, the number of non-bonding, we had 2. The electron domain geometry is how many domains do you have? An electron domain has to do with either bonding or non-bonding. Why do we say 4 electron domain for each tool? Let's look at figure F. If you look at figure F right here, this is the domain for the lone pair. This is another domain, this another domain, this another domain. So we count even unpaired electrons as domain. These electrons right here is a domain. Whether it is a double bond, triple bond, we count as a single domain. For a molecule such as this is 1 domain, this is another domain, so we talk about 2 domains. This has 3 domains, this has 3 domains. This is a domain, this is a domain. So when you have, for water molecule, we have 2 lone pairs, 2 non-bonding pairs, and our bonding pairs giving us 4. So if you are using this table, it works as the other one, that we have 4 domains, and the electron domain is tetrahedral. Non-bonding, we had 2, non-bonding, and two bonding, and the bond angle we use like that. So you can reconcile with the other table. You can reconcile with the other table, this one. The advantage of this is I do have this, and you can look at the shape. The only thing I don't see here is the hybridization, which you need to use this to predict. So the two tables, that is table 2, you'll only have to come back here to specify the hybridization of your molecule. So for H2O, we say it is sp3. So if I was to go back to the data sheet, the hybridization here is sp3. You see this is sp3, and I don't want to get in details what sp3 or how to megamolecule should have covered in details in the lecture. Hybridization, mixing of orbitals so that chemical bonding can take place. Now, let's see. I've done this, I've done that, I've done that, I've done that, and I've done that. And the remaining, all right, the remaining 2 items right here, formal charge, there is a note, all right? There is a note on how to find the formal charge. There is a note on how to find the formal charge. And I don't want to, you know, to just code the same way, you know, here it doesn't really explain much, you know, how the equation look like or which one, you know, formal charge, original minus assigned electron. This is totally different. Let me erase here and derive an equation which is much easier than what we are given here. Look at the equation. Instead of using this, all right, instead of using this, I will give you an equation which will work. And it's easier to remember. And this is the equation. This is the equation. The equation is formal charge, that is Fc, is given by the valence electron, or let me say number of valence electrons on an atom minus a non-bonding electrons. That Ne is non-bonding electron, all right, minus a half, maybe I should write it complete, non-bonding electrons on the atom minus a half bonding electrons. This equation here is much easier to follow in my view. I don't know if you can still use the above one right here. If I put next to each other, I don't know if it makes sense. This is what the author suggests, but this is what I find it much easier to assign the formal charge. So if we have H2O, let's see. If we have H2O, remember the molecule look like this. Remember the molecule, we had H, and this is bonded to hydrogen with oxygen, hydrogen here. If we are finding the formal charge on the central atom, we will have to apply this equation. All right, we will use the equation here. Formal charge on oxygen is number of valence electron is 6. Just assume that you are looking at the periodic table. Don't get distracted by the lone pairs of electron on either side. No, don't get distracted by the bonding electrons. Just assume that it's oxygen of the periodic table, it is on group 6, so its valence electron is 6, minus non-bonding electron, not pairs. You count number of electrons on that particular element. If I look at this, 1, 2, 3, 4. So I'll say 4, it is non-bonding. non-bonding. How many non-bonding? 1, 2, 3, 4. Minus a half bonding, a half of, maybe I should have just erased this so that we don't get confused with the bonding and non-bonding. If we say a half, I will put this in parentheses. A half of, all right, a half of bonding. You see this half of bonding electron. You now count the lines. How many lines are hooked up to that element or to the central atom? If I see here, 1, 2, there are 2 electrons right here, there are 2 electrons here, and a half of 4. So half of 4, this is will stand for this part right here stand for that in the equation. In the equation, half of the bond. 2 and 2 will go. We are remain with 2. So this is 6 minus 4 minus 2, and this is 2 right here, and the formal charge is 0 on oxygen. So this is how you'll find the formal charge. If you want to use this, what is given in the text equation too, that's fine. But the problem is, how do you figure it out? What is this a sign? You know, like a sign, what do they mean by a sign? I don't know what it is. But if you know, you can relate on how to find the formal charge, all right? And say original, you know, when say original, is it original, the 8 ones or what? No, it is just this one, valence electrons for that particular element minus the assign. Remember, not all elements will have central atom. Let me show you that. Not all elements will have central atom, or not all compounds rather will have central atom. It will be a particular element in question. So if I'm calculating the formal charge, look at the data sheet. On the data sheet, for example, carbon monoxide, right here, there is no central. You know how the carbon monoxide look like? We have only carbon and oxygen. So we don't have a central atom, but the author here specify which element you need to find the formal charge. You need to find the formal charge. You'll use the same approach. So pay attention. It's not always that all of them will have the central atom. So that's how you find or determine the formal charge. You determine the formal charge. So we are done with that, and how to find the formal charge of the central atom. Formal charge of the central atom. And lastly is the polar. Remember, polar, non-polar. In order to determine whether the molecule is polar or non-polar, you have to look at the electron displacement in the molecule. A molecule can have polar bonds, but not necessarily being or end up being polar. Let me rephrase it. You may have polar bonds in a molecule, but then that molecule is non-polar. So we are talking about the polarity of the molecule, not the presence of the polar bonds in the molecule. For example, let me show you what is meant by, presence of the polar bonds, but not, but the molecule is non-polar. Methane, for example, here, all right, if I look at methane here, this is how it look like. Assuming that all these, they are perpendicular, they are 90 degrees angle. Carbon is more polar. Remember on the periodic table, hydrogen is there and carbon is right there. Electronegativity increase going from left to right on the periodic table. So this is more polar and it will pull electrons towards itself. So this is the polarity of the molecule. See how it's gonna pull the electrons. This is the direction of the electron displacement. This is the electron displacement, this is the electron displacement, this is the electron displacement, and the net is 0. We say that this is non-polar. Even though we have polar bonds, say non-polar. However, for H2O, we have oxygen, and the molecule will stay like this. Look at F. You have to look at the examples in the text. If it is AF, and see the electron displacement. This is more electronegative. Oxygen is more electronegative, so the electron will be displaced in that direction, and the net displacement will go in that direction. So this is partially negative, more electron on this side. This is partially positive, and we say that the molecule is polar. So you have to circle only one. Is it polar or non-polar? How will I know where the electrons will be displaced in order to answer this section in my data sheet? Look at the examples in the background procedure, or rather in the theory. You are given examples of the diagram, how it look like. These are the diagrams. You can predict and say, all right, if I look at these, the electrons gonna be displaced in this direction because of this side being more electronegative. This side is more electronegative, and then it's gonna go in that direction. But if everything is the same like this, we say it's non-polar. So that's what you need to do in determining whether the molecule is polar or non-polar. Non-polar, polar or non-polar. So far, that is how to determine the polarity of the molecule. Let's see if you have any question on part one. Any question on part one?
Do we need to draw resonance structures as well?
No, you don't need to draw the resonance structure. You don't need to draw the resonance structure, because resonance structure will only appear when you know something else. They were just explaining what formal charge is. Formal charge, you may ask, why do we have to calculate the formal charge when we have resonance structure and we want to know which one is more stable? All right, you don't need to do that. And I don't want you to draw the molecular geometry here that, you just have to draw the Lewis structure, which will help you in determining all the, fill in this table. For example, there are some worked examples you can refer. If you look at here, these are worked examples. For example, cyanide. For example, phosphorus trifluoride. This is how to end up with the Lewis structure. You don't need to draw, fancy and say, oh, this is going in this direction. This should be enough for you to predict the molecular geometry of the molecule. All right. So you will work stepwise until you end up with this kind. If you look at the cyanide, all right, that's how you produce or proceed with that. I've used here the neutral molecule. Suppose you have polyatomic ion, because you will deal with polyatomic ions. This is a neutral molecule. But in some cases, you will have a polyatomic ion. For example, carbonate ion. Should be able to see how you proceed with that. All right. There is a acid ion. All right. I will use sulfate ion to show you how you can proceed with that. Sulfate ion, let's see, where is my, I'm gonna look at the sulfate ion.
We can't see your screen.
Yeah, you can see the, oh, I moved out. Let me just share my screen. I'm gonna share my screen. All right, I'll share my screen. Can you see my screen now? Can you see my screen?
Yeah.
All right.
We can see it.
Yes, so let me show you how you can deal with polyatomic ion. You see this? I'd say molecule. Molecule is a neutral one, doesn't have an overall charge. What will you do with the polyatomic ion? And in this case, a polyatomic ion could be S, O, say 4 with an overall charge of -2. This is sulfate ATE. This is sulfate ATE like that. All right, sulfate ATE. And you work the same way in determining the total number of valence electrons by saying that here I have sulfur, which is 6 times 1, because we have 1 sulfur, we have 6, and 4 oxygen. So I have oxygen here is 6 valence electron for each oxygen times 4. This will give me 24. If I add up that will give me 30. And then because of 2 extra electrons, the overall charge on this right here, you add 2 extra. Remember, electrons are negatively charged. So this means we have 2 extra electrons. If it is -1, that means we have 1 extra electrons. If it is -3, that means you have 3 extra electrons. Whatever the overall negative here, such as for carbonate ion, you have a negative charge of 2. That means you have extra 2 electrons. So I'm gonna end up with 32 valence electron. This is what you will be working with. This is what you have on the table. This is what you have on the table. And you'll go back and say, all right, let me just draw the skeleton of my molecule, S, and this is bonded to 4 oxygen on this side. There is 1 oxygen on this side, and then there is another oxygen on this side. This is the skeleton. Rule number 2. I'm done with number 1 here. Number 2 here is how do I draw the skeleton? Always, for most part, the first element is the central. This one is hooked up to each one of the either side. Now we got to subtract the bonding. This term right here, bonding electron, is how many lines? There is 1 line here, 1 line, 1 line. So times 2 is 8. So I'm just gonna subtract 8. These are the bonding electrons. We call these bonding electrons. And what remain here is 24 electrons. All right, 24 electrons remaining. This is what remain. This is what remain. The first priority goes to external atoms to satisfy the octet rule, except if we had hydrogen. I don't see hydrogen here. All right. So first priority in this what remain, we are trying to satisfy the octet rule. And we start with the external atom. What is hooked up to the central? If I look at this oxygen, it needs 6 more. Right now, there are 2 electrons here to satisfy the octet rule. I need 6 more, and they should be paired. See that? They should be paired. This one should be paired as well. This one should be paired. 2 electrons right there, 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 2 electrons right there. So what I remain with is 24 minus 24 remains 0. If something was remaining, all right, if something was remaining, we will put it on the central atom anywhere. Just pair them up anywhere on the central atom and it will work fine. So we work towards the central atom. Right now, nothing remain. Nothing remain. Okay. We need to draw our box on the central atom. If I look at the central atom, this is the central atom. And using my handout, this is of this A B, I have 4 atoms hooked up to the central. A is the central, B are external atoms, and I don't see any lone, any lone pairs on the central atoms once I draw my box. So my configuration, when I consult the handout I gave you, all right, let me just save this and let's go back to the handout. Can you see the, can you see that, this handout? Can you see this handout?
Yeah.
Sorry about, it's cluttered a little bit, but let me erase this. Let me erase this so that it's gonna be clear. I'm gonna erase this. We know the configuration is AP4. This is AP4. I wanted to show you the configuration. So if I have that now, remember it was AP4. So I look for AP4 here, and this is the AP4. So I'm gonna be working with this row right here to complete my, the electron domain geometry. This is geometry of electron pairs. It is tetrahedral. Geometry or molecular geometry, it is tetrahedral. It's okay to be the same, all right? And what else? The bond angle is 109. And for hybridization, all right? Remember, this stands for 4 domains. These P4 stand for 4 domains. If I have P2E, 2 plus 1 is 3 domains. This is 3 domains. 2 plus 2, 4 domains. 5 domains. 4 plus 1, 5 domains. 3 plus 2, 5 domains. 2 plus 3, 5 domains. So here I have 4 domains with no lone pairs on the central atom. Remember, all this is a function of the central atom. So if we go back to now, hybridization and how you can read from the lab manual, all right? Let's go back to the lab manual and look at the data sheet as well. Look at the data sheet. Is it here? Let's see that. This is the table I'm looking at. And I want to look at 4 domains. Remember 4 domains? Is it tetrahedral? And there is no lone pairs. You see these no lone pairs? Tetrahedral, 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 and the bond angle is 109, and hybridization is sp3, sp3. So that's what I know. And then of course you calculate the formaldehyde the way you we did before. What I want to show you now is how do you now draw to complete, all right, to complete the Lewis structure for a polyatomic. It doesn't end like that. This is how you complete the Lewis structure for polyatomic ion. You need to indicate with the parentheses like that. We don't know where those 2 electrons are. We don't know where those 2 electrons are. You should have an overall charge of -2. You don't just leave the way it is. This is how you do cations as well. Ammonium, if you have any positive, do the same thing, hydronium. But the common polyatomic ion cation is ammonium. So you have to have an overall charge here. So if I look at or show you in the same way how you handle polyatomic ion, I think there is a polyatomic ion cyanide. Let's see, they should have it on cyanide. You look at the cyanide here. Why did they have it in parentheses? Because we don't know where the charge is. So all polyatomic ions should be represented in big parentheses with an overall charge depending or corresponding to the charge on polyatomic ions, That's what I'll do for polyatomic ions. A couple of them are in the data sheet, okay? And page 236, if you forget the chemical formula, you can look at this. What are highlighted here are the central atom. Look at the central atom, and that will take care of part one. Now, part two, let's see. Part two of the data sheet is now polyatomic, not polyatomic ion. But before I go to part two, any question on part one? Good. I'm gonna move on to part two, which is easy. First, let's see what is meant by sigma bond and double bond, or or even before I go to part two, hold on, let me back up to how to construct polyatomic ion. I talked about my rules here. There's some rules I came up with, and right here, I didn't mention about, right here, how to make a double bond and a triple bond, how to make a triple bond or double bond. If I go to part two, I forget to walk you through how do you know when to make a double bond or not. I'll use sulfur dioxide. Before we go to part two, sorry about that, I want to show you when do you end up with double bond or triple bond. If we start off with sulfur dioxide, and just rule number one, sulfur equals to 6. That's rule number one. Oxygen equals to 6 times 2, all right? And this is 12. If we add up everything here, we end up with 18 valence electrons. And if we draw the central atoms at sulfur, it's bonded to 2 oxygens, bonded to 2 oxygens. Subtract the bonding, rule number 2, we are done with, rule number 1 and 2. We can subtract the bonding electron minus, there are 2 electrons here, there are 2 electrons right there, minus 4. Whatever remain here, all right, 14 electrons remain. This is how many is remaining. So what we need to do in this remaining is first priority in satisfying the octet rule are the external atoms. And each oxygen in this molecule needs 6. So I've used 12. And this leaves me with 2 valence electrons, remaining. So whatever remains goes to the central atom, and you have to pair, don't put here, no. You have to pair them up. This is when you do the inspection, make sure that the octet rule is satisfied. Do not attempt to create electrons. Look at this, somebody might say, let me just, maybe the instructor, let me just make up some electrons so that, each element satisfies the octet rule. I just made up these 2 electrons, and it doesn't work like that, because if you do that, you'll end up with more than 18 with the molecule should have. So we don't need to create extra electrons. Just gonna erase that, and with that, we will need to.
Quick question.
Yes.
Why did you subtract it by 4 again?
Why did I subtract 4?
Yes.
Bonding electrons in each of these line right here, I have 2 electrons.
Okay. Okay.
You see that? And then I have another 2 electrons right there.
All right. Thank you.
Yeah. So minus 4. That's rule number 2. Subtract the bonding electrons. Number 3, bonding electrons right here. So for remain 14, and then out of 14, I keep each oxygen, 6 to make or satisfy the octet rule. So in order to satisfy the octet rule in this molecule, let me erase this. If you look at the molecule the way it is, oxygen and oxygen satisfy the octet rule, but sulfur in the center has only 6 electrons. There are 2 here, there are 2 here, and there are 2 here, 6 electrons. Yet we need to satisfy the octet rule. That is now when you use either of these 2 or either of these, it doesn't really matter where you get the 2. If I get rid of that, and then I'll make a double bond where I'm taking that 2 from, right here. I'll make a double bond there, and the molecules, or rather each atom in the molecule or each element in the molecule satisfy the octet rule. We have 4 electrons right here. It's the double bond, and we have 4 plus 2, that is 8. So 8 electrons, 8 electrons, and 8 electrons. So the molecule satisfies the octet rule. Sometimes you may want to go back and forth until until each element satisfies the octet rule. If you don't do this, it will affect the Formonchai calculation, all right, for the central atom, and it will be wrong. So remember when to generate or make double bond or triple bond. It works the same way for double bond, for triple bond, just satisfying the octet rule. That is how to generate a double bond or triple bond. Is pi. Once you have done subtracting and no more electron is left, and you got to go back and say, does each of these atoms in the molecule satisfy the octet? If not, then the answers are you need to make a double bond or triple bond. Double bond or triple bond. Now there is 2 terms which you need to know in terms of double bond and triple bond. Double bond and triple bond. Let's see. For double bond and triple bond, all right. For double bond and triple bond, we need to know how many sigma bonds and pi bond in double bond and in pi bond, and no, how many sigma bonds and pi bonds are in triple, and all right, are in triple bond and double bond, sigma bonds and double bond. I will share my screen here to show you what I meant by, or for you to understand. Please write this down somewhere. It's gonna help you. Can you see this? Can you see this, what I've highlighted on the screen?
Yeah.
It's saying that in general, single bonds between 2 atoms are always sigma bonds. All right, so single bond is called sigma bond. Double bond, listen, double bond, that means 2 lines. Double bond comprised of 1 sigma bond and 1 pi bond. 1 sigma bond and 1 pi bond. So here, I can say double bond like that. We have 1 sigma, this is sigma bond, and 1 pi bond. You can say this is pi bond in what? In double bond. So if I change this, all right, how about if we have a triple bond? If we have a triple bond like that, here triple bond comprised of 1 sigma bond and 2 pi bonds. So this one will contain 1 sigma bond and 2 pi bonds. This is something you are expected to know before we get to part 2. That in double bond, all right, how many pi bonds, how many sigma bonds do I have? In triple bond, how many sigma bonds, how many pi bonds? It will impact on how you will complete the data table on part 2. If I close this, let me just close this and pull up the data sheet. Pull up the data sheet right here. We are on part 2 now. You see it here? You see what's saying sigma bond and pi bond? Are you all on the same page? Can you see? Can you see this?
Yeah.
Yes, thank you. Now, in order to complete this, you have to have this knowledge here, what I just gave you, what it means by sigma bond and pi bond. You'll draw your structure. For organic compounds, such as these right here, they have long chain. Let's see if I light here. These organic compounds are compounds made up of carbon and hydrogen. Some of them will have a double bond, some of them will have triple bond. There is what we call alkane. You know what alkanes are, right? AEN. This means they have only single bonds. But if we have alkenes, KEN like that, EN, that means they must be a triple bond, they must be, let me just raise like that, they must be a double bond somewhere. And then alkyne like that, they have, this is K, Y, N, E, these are triple bonds. They have 3 bonds. So when you see here Y and E, they must be triple bond somewhere. They must be triple bond somewhere. Now, these compounds, if you look at here, it's not about like central atom or, you know, external atom, doesn't work like that. It's not like part 1. Here you have to draw the skeleton of the molecule. For organic compounds, you have to understand what subscript means. I'm just gonna come up with a molecule here. Let's say 7, and then H16, for example, H16. H16. This means I have 7 carbon, and you start by building the molecule from the carbon chain. That is, the skeleton is carbon chain. And remember, carbon form 4 bonds. Remember, 4 valence electron for carbon, and it can form 4 bonds. So for this, I'm gonna have 1 bonded to another one, bonded to that, bonded to that, bonded to that, bonded to that, and bonded to what? Bonded to that. Let me see, count. 1, 2, 3, 4, 5, 6, 7. So I have taken care of the 7 carbon I need for each carbon. And then you see here you have to use 16 hydrogens, and we know each carbon form 4 bonds. So the first carbon here will need 3 hydrogens. It needs 3 hydrogens to satisfy the 4 bonds. All right. So this one will also need 3. This one will also need 3. This one will also need 3. And I've used 6. So I've used 6 here. I've used 6 here. And remain 10. If it was 16, remain 10. And if you look at this, 1, 2, 3, 4, 5, that means each carbon will need 2. Each carbon will need 2. All right. Each carbon will need, this should be hydrogen. So hydrogen, hydrogen. This will be hydrogen. This will be hydrogen. This will be hydrogen. And this will be hydrogen, and this will be hydrogen right there. Now this one, all right, this is the structure of the molecule. If you don't have enough space here, you know, you can just use additional scratch paper to complete, but if you use a pen, you know, you can just put it in there. This is the structure for this molecule. In order to complete now here, I'll count how many single bonds I do have. And remember, the single bond is a sigma bond. Just this is called sigma what? Sigma bond, sigma bond. So I'll say that right here, how many sigma bonds I do have. I'll count all of them, including this 1, 2, you know, you count how many you have and then put it right there. And then I don't see double bond. So if there was a double bond, you have to account for this sigma bond, and then you add to whatever you had for, you know, for sigma bonds. And then for triple bond right here, if there was a triple bond somewhere here, I will just account for sigma bond, and then I add the sigma bond I had before, and then add this one, and then to give me total number of sigma bonds and the pi bond if there was a triple bond. That's how you determine the number of sigma bonds, the number of pi bonds. This is for alkene. This is, by the way, this is called heptane. This is heptane, T-A-N, heptane from heptalon, seven. Okay, all right. So that is for what? That is for single bond. How about if you have a double bond? How will I know? This one, if I look at this, all of them will be single bond because it is AEN. These are saturated. We call these saturated alkanes. That means single bond. So anywhere with AEN, but anywhere with ENE, that means you could have a double bond somewhere. If you have Y and E, you'll have a triple bond somewhere. I'll show you, I'll show you how to generate a double bond or a triple bond. First, have that key. What I have right here is going to help you. I will do this. I'm going to do this. And you'll see how easy it is to come up with your Lewis structure for the molecule. At the outset, it has 3 couples. So you have to say, all right, I need 3. 1, all right, 2, and 3. Don't try messing with hydrogen fast before you account for this E and E means it must have a double bond somewhere between 2 couples. So I can either put right here or I can put right here. It doesn't really matter. Even if it is a long one, you can put it anywhere. So if I put right here, I've satisfied the, the naming EN. That means it's unsaturated with double bond. I mean with a double bond. If you look at the number of hydrogens we need to use or to have at the end of the day, 6 of them. Bear in mind, carbon form 4 bonds. It cannot form 5 bonds. All right. So the first carbon in my skeleton needs 3. So I'm gonna put 3 right here so that I need to end up with, to satisfy the bonding, I mean the octet rule or whatever you want to call it, 4 bonds for the first carbon. And if I look at the last carbon right here, I have 1, 2. So I need 2 more. I can put it right here. You can put right. It doesn't really matter where you put. You can even put, so long as I see that there are 2 hydrogen. How do I know? It's gonna play out. It doesn't really matter. You can start with this and ask yourself, how many bonds do I need to make for this? I need to make 1, 2, 3. I need 1 more to complete the requirement for this carbon. So if I look at this, so if I count the number three, 1, 2, 3, 4, 5, 6, 7, 8. So how many couples do we have? 1, 2, 3, 4, 5, 6. Can you see that we have 6 hydrogens? 1, 2, 3, 4, 5, 6. 6 hydrogens. Because of E and E, I shall have a double bond somewhere. So you start with the skeleton first. Place your double bond or triple bond, anywhere. So long as you see the double bond or triple bond on the main skeleton, that's fine. Once you put in the hydrogens, it will play out correctly. Make sure that you don't end up with more than 4 bonds on each carbon. For anything ending A and E, that means it is saturated. Doesn't have a double bond, doesn't have a triple bond, and then you just take it from there. That will take care of, the structure. So when you count now the number of sigma bonds, count first of all how many single bonds do you have here. When you come right here, all right, when you come right here, pay in mind that this means this is what you have. This is what you have in that double bond. That double bond has one sigma bond and one pi bond. One sigma bond and one pi bond. If it is a single bond, it's only one sigma bond. If it is triple bond, then one sigma bond and two pi bonds. So that is how you account for. So if I am to count the sigma bonds, I'll say one sigma bonds, 1, 2, 3, 4, 5, 6, 7. 7 sigma bonds and 1 pi bond. For this, so 7 sigma bonds right there, and 1 pi bond. Yeah, 1 pi bond. That's what you will fill in here by just attaching that. That's what you need to do in part 2. In part 2. Any question in part 2? Any question in part 2?
No.
No. Now, the last part is easy. The last part is easy. I am going to wind in few minutes. It's not hard. If you look at, let me erase this. Somebody send, no, let's see. Jessica, you have a question? Jessica, you have a question? Oh, no, thank you. So what I wanted to say is erase, I'm gonna erase what I have here so that I walk you through the last part. It's easy. The last part is easy. I have walked you through before. When I had those sets of rules, I'm gonna send you those sets of rules again, all right? I didn't send that out, but I did send just a summary. I did send a summary of Fallon-Shell electron pair repulsion models. So here is what you need to do in the last part. It is just a Lewis structure, just the way we have been doing. First of all, the hint, acetate ion. Means if we interpret this is somehow, acetate ion, this first carbon is bonded to 3 hydrogens and carbon to carbon bonds, all right? Acetic acid, you got to look at the chemical formula for acetic acid. Hypochlorite ion, it has a negative charge. So basically here is a combination of organic and polyatomic ion. Phosphate, for example, you know how phosphate look like? All right, so here is this PO4. How do I know this? They expect you to remember. They expect you to remember how to write. Sulfate, I did this before, all right? SO4, 2 negative, all right? You got to look at the chlorus ion, hypochlorite. It's given, all these ion. You got to look at the text right here. It's given here. Chlorus ion, acetate ion, acetic acid. You got to look at the, or you can use text or any other resource. If I look at this, just mention here acetate ion and acetic acid. Acetate ion and acetic acid. You got to draw and just complete the Lewis structure. You don't need to calculate in this part. You don't need to calculate the formal charge or it's just the structure. And you can submit the walkthrough, submit through the Canvas on the respective folder. Jessica, you have a question? Jessica is saying she doesn't have a microphone. The final exam, yes, it is multiple choice, yes. Jessica is yes. I will send you more information, what you need to, before I wind up, I'll send you information for the final exam, what you need. If you need to print out, you got to print out. I'll look at the question, what you need, solubility chart, and any other relevant material, such as periodic table. Of course, have a scratch paper somewhere to do your calculation. And other than that, I want to thank everyone for joining in today. I really appreciate. I know it's a rough time. They are trying to cope with, you know, what's going on. Hope we will get over this in a few days. Maybe I want it to be as soon as tomorrow. This is just, you know, I miss just being in class and doing stuff and mixing stuff and see how the reaction goes. Other than that, the class is dismissed. Peace safe. I'll see you next week. If you have any question, please send me an email. If I don't respond right away, maybe I'm in a meeting or I'm in another class session such as this, but I'll try to help you. Sometimes for those who, you know, who need one-on-one assistance, you can come during office hours and I can just be live. We can go one-on-one on any, address any concern you may have. The class is dismissed. Thank you. See you next week, Wednesday, same time.